this is a lesson on formal charge, which formal charge is a value or a tool that we use, a value we calculate to assess which Lewis structure is best for a given molecule or polyatomic ion. So there's an equation for formal charge, and if you look it up on the internet, you look at it in a textbook, it'll probably be presented like this or something similar to this. This FC refers to formal charge, and formal charge is a value that looks like a charge, like it's like +1, +2, -1, -2, or 0. It looks like a charge, but it's not actually a charge. It's kind of a make-believe number that just helps us know how stable and energetically favorable an atom is in a certain Lewis structure within a molecule. So it's just a number that we assign to each atom in a Lewis structure that helps us know if that Lewis structure is most likely the correct one or the most likely one. So it's not even really a charge, to be honest. It's a bit of a misnomer, but it looks like a charge, so probably that's why they call it formal charge. Formal charge for any atom in a structure is V, which is the valence electrons, and this would be like the original valence electrons that a certain atom would have. So the original valence electrons of the atom minus the lone pair electrons that still exist on the atom when it's in the proposed structure, minus the bond pair electrons that exist for that atom in the proposed structure, divided by 2, okay? Sometimes the formula, you'll see various teachers online on YouTube, etc. Sometimes they try to simplify this formula, and it might work for you to think of it this way. I'll show you both ways, and then you can decide for yourself. They just changed the formal charge formula to what an atom should have, how many electrons an atom should have around it, minus what it actually, so what it should have, minus what it actually does have around it. And it's kind of not, I have to show you an example to explain what that means, but it's kind of talking about electrons immediately around the atom. Alrighty, so let's start with a relatively straightforward one, which is CH4 methane. Again, I'll just go through the process of how I would recommend you come up with the Lewis structure for this if you're just kind of starting out of the blue. So you would look at how many valence electrons each atom in the structure has, because those are the electrons you need to show in a Lewis structure. A Lewis structure shows valence electrons. So a carbon atom has 4 valence electrons, and each hydrogen has 1. There are 4 hydrogens in the structure for a total of 8 electrons. So in this Lewis structure, we're going to have to show 8 electrons. All right, so you always start by putting carbon as the central atom if carbon's there, and it has to bond to each thing at least once. You count the total electrons in the structure, and there, you're going to see you've got 4 bond pairs, so 2, 4, 6, 8 electrons. No need for any lone pairs, no need for anything fancy. So that is obviously the correct Lewis structure for methane. Now we go and assign formal charges. And what's the big idea with formal charges? The idea is that if formal charges, the closer they are to 0, so maybe I better write this out. The formal charge, when we calculate it for each atom, the closer it is to 0, the more correct we know the proposed structure is. We basically want to be having these values be in low of a magnitude as possible. Okay, so let's go ahead and calculate it. So for carbon here, we would say, again, for the formal charge of carbon, it is, well, first write out the kind of big ugly formula. Let's see how you like that one. The number of valence electrons in carbon is supposed to be 4. The number of lone pairs for carbon in this structure are 0. There aren't any lone pairs. And the number of bonding pair electrons for carbon in this structure is 8. Divide that by 2, we're going to end up with 4 minus 4, which is 0. And that's great. That's what you want your formal charge to be. That's the best it could turn out to be. Let's do the same thing for each hydrogen. Each hydrogen is the same in the structure, so it's going to look the same way. The number of valence electrons in a hydrogen is supposed to be 1. Naturally, there are no lone pairs. Each one has 2 bond pairs. So you're going to end up with 1 minus 1, and that's a 0. And so that's great, and that tells us that this is indeed the correct Lewis structure for methane. Now, what if you want to do it, if you want to use the alternative equation for formal charge, the whole, what it should have minus what it has, should minus has, let's say. So let's do it for carbon. Carbon, we would say, generally should have 4 electrons around it. And in this structure, by this method, we say, oh, it does have 4 around it. What the heck does that really mean? Because to me, it looks like it has 8 around it, 8 in its valence. That's not what they mean by this. What they mean is, like, imagine each of these X's is actually the electrons around carbon. So now it has 4 around it. So it generates a formal charge of 0. Or for hydrogen, if you look at it that way, you might say, all right, it should have 1 around it. It does have 1 around it. I'm going to draw the hydrogen electrons as little circles. It does have 1 next to it, so therefore its formal charge is 0. I'm not really a fan of the abbreviated version. I think it's a little bit more transparent to use the full version of it, but up to you. All right, so let's kind of do a tough one here and see, and I'll show you how formal charges can help us get to the right place here. So let's say we've got the polyatomic ion nitrate, and of course this is one of the polyatomic ions that in the IB diploma program you're supposed to memorize and know the formula of. There it is, it's nitrate. Let's do its Lewis structure. How many valence electrons? So we're figuring out the valence electrons in the whole structure. That's what we need to show. Nitrogen has 5. Oxygen has 6. There are 3 oxygens. That's a total of 18 plus 5, which is 23. And then we're going to add that extra electron here to the total valence. Have another electron. And that's 24. So in the structure, we need to show 24. We're going to put the nitrogen there with 3 oxygens around it. We're going to start from there. We have shown 6 electrons in the structure. We have to add another 18. That's going to be 9 lone pairs. So it seems kind of natural then that we're going to stick those lone pairs, 3 of them around each oxygen. And ta-da! Is that the proper Lewis structure for nitrate? Well, we should have one of these too if we're doing it right. Is that the proper Lewis structure for nitrate? Well, we can show through formal charge that it's not actually the best structure. There's another little tell here that shows you it's not the best structure, and that is if you look around nitrogen, you can see that nitrogen is not meeting the octet rule here. It only has 6 electrons around it. So let's do formal charge. Formal charge of nitrogen in this case, okay, is it would naturally have 5 valence electrons. How many lone pair electrons does it have? It doesn't have any. How many bonding electrons does it have? It has 6. So this is 5 minus 3. It has a formal charge of plus 2. That's not 0. So that's not really that great. Now let's analyze each oxygen. Each oxygen is the same in the structure, so it has a formal charge of 6 is how many electrons they should have. There are 6 lone pair electrons as well, and there is 2 bond pair electrons. So this means each one of those has a formal charge of minus 1. Okay, so each oxygen, according to this proposed Lewis structure, would be a minus 1, and nitrogen would be a plus 2. That's not the best. Okay, we want zeros, we want low numbers for this. So let's make a couple of changes. Again, we had it this way. Okay. Just a second here. We had it this way. Okay, and I'm going to propose to make a change based on those high formal charges. Okay, what if we take one of those lone pairs and turn it into a bond pair? So we're going to get rid of this lone pair here and make it a bond pair. All right, what does that do to the formal charges? Well, for one thing, if we now look at nitrogen, its formal charge goes to down to +1 instead of being +2 where it was before. Okay, so that is better. Oxygen, now this oxygen goes down to a 0, I believe. All right, we had 4 lone pair electrons. We have 4/2 for 2. That's a 0. Okay, so that's good. Each of these remains a -1. Now you might say, well, can we make it even better? There's not much else we can do. We can't really take another one of these lone pairs and turn it into a bond pair, because then that would be saying that nitrogen has an expanded valence of more than 8, and that's not something a nitrogen atom can do. So this is probably the very best we can do. We reduced the formal charges from being -1, -1, -1, +2 to at least being +1, a 0, -1, -1. So overall, we got each of those respective formal charges as close to 0 as we could, okay? And then, of course, if this is the actual final structure for a nitrate ion, it's going to have a delocalized electron situations. So we're going to have to actually show the 3 potential variations where the would-be double bond is either in location A, location B, or location C, right? Like, which one of these oxygens is it going to be on? We don't really know. And of course, as a matter of fact, we know that it doesn't actually, you should understand, it doesn't actually exist on one place or the other. Those electrons kind of get shared throughout the molecule, and this would be a classic example of a delocalized 1.3 bond. Okay, it's like a 1 1/3 bond that exists between the nitrogen and the oxygen here. Hope this helps.